Generative hand tracking algorithms register a geometric model of the human hand to sensor data. Tracking quality depends on how well the model fits the user being tracked. State-of-the-art tracking algorithms calibrate by jointly fitting a model to a small set of input frames. Current solutions require the user to select these frames manually while tracking with an uncalibrated model, and then wait for the calibration algorithm to finish. Multiple frames are strictly necessary as no single pose contains all the needed information. We can see that to regress a given parameter, there are good and bad poses. But how can we detect these automatically? If this is possible, can it be used to get rid of offline calibration sessions? Let us abstract a finger with a simple 2D stick figure. Our registration energy is the sum of closest point distances. When the finger is straight, the energy does not change much as we vary the length of the phalanx. When the finger is bent, the energy becomes more sensitive to changes in shape. The Hessian of the registration energy, the dashed line, captures the width of the valley in the energy landscape. In more detail, the Hessian defines a Gaussian capturing the uncertainty of the estimate. Let us look at more poses of our 2D stick figure. For a given pose, we can compute the Hessian, here illustrated with ellipses. These ellipses encode precisely the uncertainty we seek to represent. But how can information from individual frames be integrated through time? Each frame represents an estimate via a Gaussian distribution. When multiple observations of a variable are made, the cumulative probability is obtained by multiplying their distributions. Thus, estimates from different frames emerged by multiplying the corresponding Gaussians. We approach generative tracking by using a sphere mesh as a geometric representation of human hands. Sphere meshes consist of a skeletal graph with sphere radii defined at each vertex. These models are well suited to compactly represent human hands. Let us now verify our mathematical formulation on a full 3D example. Consider the Hessian entry corresponding to the middle phalanx of the thumb. When the thumb is bent, certainty is high. When the thumb is straight or occluded, certainty is low. In poses with high certainty, the estimated value is also closer to the correct value, and this allows the algorithm to converge towards a good estimate. The same holds for other ambiguous degrees of freedom. Here we show the per frame and cumulative estimate values, as well as per frame and accumulated certainties of a few hand-shaped parameters. Our online calibration relies on an algorithm that can accurately estimate a shape parameter when the model is in an unambiguous pose. However, as this algorithm works on a per frame basis, shape parameters can oscillate widely over time. On real data, the behavior is similar, but notice how this allows the algorithm to handle the tracking of different people. We now present our complete online calibration algorithm. Here, the surface of the model is color-coded to visualize certainty. We also display the per frame and accumulated certainties in time. In the beginning of the sequence, all the parameters are uncertain. Their confidence grows as information becomes available. Once certainty reaches a predefined threshold, the calibration phase is complete. The remainder of the sequence is tracked with a fixed personalized model, making the tracking faster and more robust. We stress test our system by qualitatively evaluating our calibration technique. Data is acquired from 12 different users performing in front of an Intel RealSense SR300 camera. Enjoy the next 3 minutes of recordings. Thank you for watching.